Okay, so first of all, thank you very much to the organizers for having me and for the lovely lunches. That was a lovely surprise. I'm here to talk to you guys today about quantum simulation in multi-qubit phase space. There's a link to the archive for those that are interested in just skim reading directly what it's doing. The main motivation behind this work was that quantum mechanics admits many different descriptions. We've just seen a talk about digital versus analog representation of quantum dynamics. And actually, the mainstream description, arguably, is that based on Hilbert spaces. But for many body physics or multi-qubit systems, this hits some issues. The two that we kind of really suffered from as deep learning practitioners in ICFO was the curse of dimensionality in Hilbert space, the scaling of the number of coefficients you need on a fixed basis to represent an n-body qubit system, and the urge, craving, the want to apply contemporary deep learning tools in many body physics, kind of beyond the simple multi-layer perceptron and neural network-based architectures and starting to move towards some of the more flow-based or generative processes that have really transformed other sectors in the last 10 years. So what I'm going to talk about, therefore, is in 20 minutes to try and construct a phase-space formalism for multi-qubit systems that is faithful to the postulates of quantum mechanics, and then, if time allows, discuss some of the computationally favorable prospects that this offers for deep learning architectures. As a kind of hint to where we're going with this, the useful property that spin phase space has is it kind of manifests the curse of dimensionality differently. Most notably, when you write down a quantum state in its Hilbert space representation, you have this kind of O2 to the n representation complexity for the coefficients of that state. But interestingly, you can construct density functions, in other words, a scalar representation of the quantum state on a special type of spherical coordinates, which we'll talk about in a second, which scales linearly in its input size for the number of systems, which I think is super cool and kind of odd. And somehow the curse of dimensionality is still going to persist in this second representation, but in a way that is more amenable to deep learning. So I'm going to break this talk down into 3 sections. We're first going to talk about the Stratonovich-Weyl correspondence. I'm then going to talk about how it extends into many-body quantum dynamics, and again, as time allows, a bit of prospects for deep learning. So, without further ado, the Stratonovich-Weyl correspondence is essentially an invertible mapping between objects in a Hilbert space and density functions on symplectic manifolds. And it kind of has 2 flavors. The typical and very much well-studied flavor that this comes in is in quantum optics, where functions like the Husimi Q function you can see on screen, as well as the Wigner function and the Glauber-Sunderson P function, are a kind of workhorse for analysis in these continuous variable systems. And they have a lot of really nice properties, signatures of non-classicality, Gaussian quantum optics works really well here. And yet, despite how pioneering this kind of set of tools was in quantum optics, the one for spin systems was little explored when we were going around looking for one. It was unclear how it extended into a many-body representation. And we think, or at least we kind of conjectured last year, that this could solve the problem of taking gradients in Hilbert space as well as sidestepping the curse of dimensionality in an effective way. So how does this work? Essentially, what we're going to do is construct this invertible mapping between, say, positive operators on some n-qubit Hilbert space and these functions, which are maps from our symplectic manifold onto the reals. And the way to do this is to start with a parametric state, a coherent spin state, which you can see on the top, and then realize this mapping by contracting, so tracing your density matrix on a family of S-parameterized kernels. Now, this kernel is just an outer product between our coherent state and some multiplicative factor of the identity. But notice, when I perform this trace parametrically, so as a function of theta and phi, this trace becomes a map from these 2 parameters, theta and phi, to the reals. In other words, it looks a lot like a phase space function. And this S here is just a parameter that allows you to move or interpolate smoothly between the 3 representations that are well studied in quantum optics. These are the Q function, the Wigner function, and the P function. And actually, in our research, we found that the most interesting state, at least we think so far, is this Q function. And the reason that we really liked this specifically in terms of making a phase-space contraction was that it's positive and it extends really cleanly to multi-qubit systems, which, as this was the aim of our work, we thought, okay, let's go with this one. So actually, it doesn't just work for states. There's a whole dictionary you can use to translate everything that you might want to do in Hilbert space into its phase-space representation. Now, in 20 minutes, I'm not going to go through all of this, but essentially, there's a way of faithfully mapping between operators. There's a way of kind of embedding a Lie and Jordan algebra into this, as well as doing inner products, tensor products, partial tracing, and all of the various things we physicists like to do. So, to kind of build a little bit of intuition for this Q function, because I appreciate right now it's just this abstract contraction, I want to talk about 3 examples: the Pauli eigenstates, the thermal mixed state, and the Bell states. So let's start with the Pauli states. Here you can see the Pauli states visualized by essentially projecting the coordinates down onto the plane, and this is a periodic representation, so I haven't done some sort of projection here. This is, you've got to wrap the y and the x boundaries around each other to really see this as a spherical density. But you can see some pretty nice things here. First of all, the x and the y eigenstates are, no surprises, shifted with respect to each other, and the z one is special just because of our choice of coordinate systems. So yeah, that's the Pauli eigenstates. I also think they just look really pretty. It's nice to see it as a full density. Next, thermal states. Interestingly, you can also represent mixed states, which means there's a route to entanglement later. Here you have 4 thermal state densities of the Z operator, starting with beta goes to -infinity, so fully pure, all the way down to the maximally mixed state you see all the way on the right, which is just a completely uniform density over my spherical coordinates. And as I turn the temperature up and down between these 2 limits, you can see different amounts of thermalization in this representation quite clearly. And lastly, I want to talk about the Bell states very quickly to kind of convince you that this is a faithful representation of quantum theory. We can write down the famous maximally entangled 2-qubit states. Okay, it's a bit clunky on a big presentation screen, but there are 2 things I want you to notice. First of all, it's not separable into local density functions. In other words, we have a genuine notion of entanglement here. There's no way I can write down any of these functions as the product of 2 functions of local spherical coordinates. And second of all, if I integrate over one of the densities, I get the maximally mixed state in the other system, just like you would have done if you were partial tracing back in Hilbert space, which is also a pretty nice property. Okay, so with that, hopefully we have a little bit of intuition for how states work. I want to move on to dynamics. So this correspondence, this way of contracting between Hilbert space and these density functions, also extends naturally to commutators and anti-commutators, as we kind of saw in this big long dictionary. But most importantly, the tensor product condition and the commutator condition match up really well. And what that means is, if you have some sort of dynamical equation which uses Hilbert space operators under commutation or anti-commutators, these become essentially differential vector fields on my spin configuration manifold, S2 to the n, which is nice because then I can, instead of trying to do kind of solutions of wave functions back in Hilbert space, I can start to think about using PDE solvers on a system of coordinates that scales linearly in the number of qubits. So these differential vector fields, I'm not going to go too much into detail, all the details are in the preprint, but essentially this gives us a piece of mathematical machinery to directly simulate how states might evolve in phase space with no further references to Hilbert space needed. And just because I thought it looked really cool, I want to show you a couple of examples of this. So the first one is real-time evolution. So here you have an initial boundary state, which is the plus state, and we're going to rotate it using the Z operator. And as expected, it goes around in the azimuth direction like this, with some period, which I've just done in natural units so that the GIF doesn't move too quickly. But real-time dynamics is not the only equation of interest. You can also do imaginary time. For those that have never heard of this technique, in the length of a metro stop, imaginary time is a way of evolving a system towards its ground state incrementally. The idea is inside the exponential of, say, e to the minus ith, you make time imaginary, and this suppresses all of the states that have high energy, in other words, that rotate quickly, much faster than the ones that are lower. So you can create a little recursive scheme that extracts out a ground state. And we can also do this in phase space. So you can actually start using this formalism to try and compute ground states in different problems. We can also do open system dynamics. Here, just to kind of show thermalization, I've switched to Hamiltonian off. I've just got a jump operator which kills the off-diagonal terms starting in a plus state. And so you can see at the beginning of the animation, we're in the Pauli plus eigenstate, but by the end of it, once the system has thermalized, we end up in the Z eigenstate thanks to this jump operator. And it's nice, you can kind of see how exactly this is working in phase space between the two boundaries. But most importantly, since we want to be able to do many-body physics, not just one-qubit dynamics, it's many-body compatible. To show you a brief visualization of how this works, we picked the ZZ operator for a Hamiltonian, starting off in the plus-plus state, which means we should be rotating from a fully separable state to a maximally entangled state and back. In Hilbert space, that would be what these dynamics would give us. And in phase space, we see exactly this. In the two right-hand panels, you can see the local coordinates for qubits 1 and 2, and they're oscillating between being maximally mixed and being Pauli eigenstates. And as hopefully people in this audience know, when you have two maximally mixed local states that you acquired by tracing out the coordinates, that means they're entangled with each other. So actually what you're seeing here is the dynamics of them entangling and unentangling and entangling and unentangling back and forth. You can also see this is non-separable by taking a phi1, phi2 slice of this 4D density and just, you can see on screen this is not resolvable into two local functions in time. So these are genuinely mixing. And last but not least, since this works very well for quantum optics already, and all we've really done here is build the machinery for finite dimensional Hilbert spaces and spin systems, we thought it would be interesting to also look at light and matter interactions. So specifically, we took the Jaynes-Cummings Hamiltonian, which preserves one excitation of the field between your bosonic side and your spin side. You've got a free field term on the left there. You've got a spin excitation with omega A, and then you've got this field spin coupling term. And if you initialize the system with a single excitation, so in other words, one excitation of the bosonic field but no excitation in the spin system, this Hamiltonian should move that quantum of energy between the field and the spin back and forth. And actually, again, you can see this really clearly in the phase space representation. On the top panel, you've got the field coordinates alpha and alpha star, say for the Husimi Q function, and those go back and forth between the vacuum state, which is this little Gaussian centered on the origin of that figure, and the ring, which is the first Fock state. And on the lower panel, you can see the energy being exchanged in the spin state because it starts in the 0 eigenstate and ends up in the 1 and oscillates back and forth in the lower one. And then to really see where this energy is going and where that probability mass moves, we can plot two of the field coordinates from the boson with one of the spin coordinates, just to actually really see how the probability mass moves around between the spin and the field. So hopefully these kind of 4 or 5 examples should convince you of the fact that this is a faithful representation of quantum mechanics. It also looks really pretty, but I appreciate that's not a good enough argument to try and employ this representation. So what I want to do next is talk about why we should use this and what the prospects are for a phase space representation in deep learning, why we should bother to actually switch machinery and maybe walk away from the Hilbert space representation. So phase space has lots of properties that make it very, very machine learning friendly, as we worked through in the archive preprint. So the first one is it's completely consistent with multipartite states, dynamics, and even purification and dilation. The full details of this diagram are in the preprint, but again, in the length of a metro stop. The idea is on the inner rectangle, you have the Hilbert space representation, and on the outer rectangle, you have the phase space representation. And what we've managed to prove with this diagram is that we can indeed take anything that was previously in Hilbert space, get it all into phase space, and never have to go back. In other words, the properties that we then get in phase space never rely on Hilbert space anymore, and it's still faithful to the postulates. The other thing that's nice in phase space is estimation. So specifically, phase space functions have this really nice duality property, which opens an avenue for Monte Carlo-based sampling schemes. This is very reminiscent of the work that Giuseppe Carleo and Felipe Vicentini did on neural quantum states over the last decade. But also, thanks to this duality and the ability to make moment-generating functions, these MGFs, you can also do expectation values by automatic differentiation. In other words, you can start using autograd from your favorite machine learning libraries to actually compute EVs, instead of waiting around for some sampler to converge to the error that you're willing to put up with. But lastly, and by very much not leastly, the curse of dimensionality manifests really differently. And actually, in the interest of time, I want to focus specifically on why this property is most important and what it gives us. So, as I kind of showed you in the preamble, if we have a state in Hilbert space, we've got these O2 to the n coefficients to enumerate how much amplitude there is in this exponentially large basis, whereas these phase space functions were maps from collections of different two spheres to the reals. Naively, this looks like I only need 2 times n inputs to then spit a real number out, and therefore that I've kind of magically got some free lunch, which obviously I have not done. So where does this curse go, and why is it different in phase space? Essentially, Hilbert space representation has an exponential number of coefficients, sure, but you take that exponential sacrifice for the gain of it being a linear function of each coefficient. None of these c's are ever squared. There's no sign of them. There's never any exponential. It's genuinely a linear function of an exponential number of those coefficients. Whereas in phase space, you get a linear number of coordinates, but the function becomes nonlinear. So you're sacrificing the linearity argument that you might want to have in your dynamics or your representation, but you're doing this sacrifice in order to then not need an exponential basis to enumerate the whole state. And actually, if you look at the span or the support in density functions of physical quantum states, you'll find that the support in the harmonic basis is still exponential. So actually, the curse doesn't disappear. It just kind of gets recast into the harmonic support of the phase space density function, rather than being explicitly manifest in the number of coefficients you need to enumerate a quantum state. Now, why do this? I feel like we've bent over backwards to get all this to work. Well, as it turns out, for quantum machine learning, this is a really, really useful property. And the argument as to why this is actually quite simple. If I give you a neural network, would you rather learn a linear function of an exponential number of parameters or a nonlinear function over a linear number of parameters? And any deep learning practitioner would tell you definitely the latter, since neural networks are nothing if not nonlinear function approximators. Okay, so to summarize, there is a well-known Stratonovich-Weyl correspondence for 1 qubit, and actually it was very well studied in quantum optics. We extended it to find multi-qubit configuration densities and proved that it is a faithful implementation of many-body quantum dynamics that comes equipped with all the things we need to satisfy the postulates. And in doing so, we have enabled a family of many-body spin phase space representations with properties that we believe are very well suited for deep learning architectures like very deep neural networks, the kinds that you might find in large wave function models or large language models, but also in some of the more generative directions like diffusion models and normalizing flow-based models. So we're now kind of on the applications phase of this theory, and we're currently working on a few different active projects to do with quantum simulation, tomography, and Hamiltonian learning. Okay, so kind of looking forward, these are these kind of projects that we were talking about, and roughly an idea of where we might go in terms of direction, but we think that there are lots of other applications. To be honest, this is an early work. It's still in peer review. We submitted it in July, but we're super excited about it. So yeah, thank you for listening.
Thank you, Tim, for this very nice talk. So we have time for questions. So I have a question. So could you give us an example of application of this equivalence between phase space? So you mentioned that it would be nice to use it in machine learning, that you are now studying possible potential applications in simulation and other topics, but can you give us a concrete example?
Yes, so something we submitted and got rejected by NeurIPS, and we're now kind of working towards making it a bit better, was the real-time simulation of the quantum Fourier transform on 20 qubits in this formalism, and we could do so with about 99.7% fidelity, and that's 99.7 over the whole 20-qubit array, not over the 2 qubit gates that it consists of. In other words, with 99.7 or 8% accuracy, we could get the correct output density of the quantum Fourier transform. We've also done cluster state preparation in order to try and create resource states on which you can then do measurement-based quantum computing. We are looking into ground state preparation problems using imaginary time. And lastly, on the tomographic side, we're using normalizing flow architectures to solve the tomography problem with a generative architecture.
Thank you, Tim.
Thanks for the great talk. It's very interesting. So I have a question and a curiosity. The question is, how does the equation for the time evolution in the phase space look like? Because it's not going to be like the linear Schrödinger equation, I guess. And the curiosity, maybe I ask you later.
Yeah, happy to do some like chalk and talk later if you want to like get into more detail. Okay. The long story short is whenever you want to take a non-commuting algebra and embed it into a scalar commuting space, you have to do some sort of pre-specification of the ordering of your operators in order to make it faithful. This is known as the ordering problem in quantum optics, and Wick's theorem guarantees that you can resolve it. There is a similar result for spin systems that allows you to essentially define a Moyal-style bracket algebra under the tensor product. And all of this, because this is like a bunch of jargon in a talk, but all of this is in, I think, proposition 9 or 10 of the preprint. So specifically how to derive a dynamical equation of motion, knowing its commutator or anti-commutator structure from the Hilbert space category.
Okay, and just very quickly, the curiosity was like, if you were to simulate quantum annealing in the phase space, how would the vanishing gap appear?
The what appear, sorry?
If you have a vanishing gap due to a quantum phase transition, for instance, in quantum annealing, would you be able to recognize it at the level of phase space?
That's a really good question. Off the top of my head, I don't know, actually. Something that we are still unsure about is how to measure the signatures of different phases in many body systems. To be honest, I don't know how to do this yet, but I'm looking forward to finding out.
Thank you. We have time for one last question. If not, so let's thank Tim and all the speakers of this session.